So let me briefly introduce you meanwhile.
Very briefly.
Let's see. Professor Dr. Osman Teoman Turgut has graduated as a double major in physics and in electrical and electronics engineering departments from Boğaziçi University in 1990. He obtained his PhD from University of Rochester in 96 under supervision of Saradaji Rajiv. He became one of the first EPDI postdocs, 1 year at IHES Burası Rivet and 1 year at Cambridge University. He had postdoctoral research position in QFT program at Mittag Leffler Institute and became a Gustafsson Fellow at KTH between 2000-2001, and then he joined the physics department of Boğaziçi University. He also worked at Feza Gürsey Institute between 2001 and 2011, and he was also the director of this institute from 2005 to 11. His awards include Sedat Simavi Award, Tuba Award, and TÜBİTAK Encouragement Award. His research interests include mathematical aspects of quantum field theory, gauge theories, geometric methods, geometric quantization, singular problems, and renormalization, and so on. Or as he likes to address it, he works on some part of mathematical physics. Yes. He has been in Carnegie Mellon University as a long-term visitor since 2018, and we are very happy that he came back and accepted our invitation to give a talk this year. So you can start if you're ready, Hocam.
Yes, well, thank you very much for this very kind introduction. And thank you for inviting me for my modest contribution to this beautiful meeting. And I'm so happy to see all these younger colleagues giving these wonderful talks about exciting subjects. And I'm going to give you a sort of a talk in somewhat old school subject about the existence of Hamiltonians for some singular systems. And as I said, I'm using a slightly low-tech approach because I wanted to share the figures on the site. So let's see. I'm going to just give a very short sort of introduction to constructive field theory. This is one of the things that is what I'm talking about is essentially related to these ideas. Constructive field theory basically began right after the triumph of QED, and people were excited that one can get actual results from this perturbative methods. But of course, there was this ideas of right after quantum mechanics, mathematicians were very much involved in developing the mathematical aspects of quantum mechanics, and they actually people like von Neumann and also I think Gelfand in Russia, von Neumann in the West, they basically start laying down foundations of these mathematical foundations of the subject, and it was natural for them to move and make the next step. And there was one subject which is called algebraic formalism, led by Haag, Kastler, Araki, and many other people. And this was a very ambitious construction. About the same time, there was this Weitmann axiomatic approach, which was giving meaning to the correlation functions in field theory. And about the same time, there was right after Weitmann and algebra. I mean, all these things are still going on. They're not subjects that people left, but they're all much more sophisticated things are being done. And I'm not an expert on these things. But then there was also in 70s direct Hamiltonian methods, constructing the vacuum, time evolution, and actually removing, basically all orders, constructions of fields, basically led by Glim and Jaffe and Simon, and there are other people, of course, but my main thing is Glim and Jaffe was the major figures in this subject. And this is essentially in the spirit of Glim and Jaffe, if you like, what we're trying, what our modest attempt is in that spirit. And about, I mean, they managed to do two-dimensional theories. Three-dimensional theories became somewhat challenging, and that was later they switched to Euclidean path integral point of view, which essentially independently, this Euclidean point of view, correlation functions in the Euclidean space called Schwinger functions, that the axioms for them were laid out by Osterwalder, Schrader, and how you link them to Weitmann perspective. But about 70s, a revolution happened, and the revolution is renormalization, and what is meant by quantum field theory. And that was basically, the major figure was Wilson. And then people realized that these ideas have to be incorporated into this rigorous formalism, and some change of perspective happened. And bunch of people, I'm just mentioning here, some of the people I know the names of. There are others, of course, and I may be I'm not completely just about giving the names, but these people, Balaban, Gavatsky, Kupianin, Galavoti, Copper, Senio, and many others, Rivaso, they start developing this perspective. So in a way, the excitement in quantum field theory and the success of mathematical approach in quantum mechanics pushed people to an over-ambitious project of developing a very rigorous formalism, and didn't exactly succeed. And because there were missing pieces, physically missing pieces, which basically explain, I think, by Wilson and people around him. So this is just to put things into historical perspective. Now, what I'm about to present is not comparable to these ambitious projects. What we will do is something much simpler, but as I said, in the spirit of Glim and Jaffe. And the modest attempt is some singular problems. They're a good testing ground for ideas in field theory. And one of the things that we would like to study, this is something that people worked a lot, the delta function potential, which you can see here. And the reason that we work on a manifold is one, that you can do it nicely with the geometric structure, as well as the fact that the geometry and the interplay between the geometry and fields. This is not a field theory problem. This is a quantum mechanics problem, but it has a singularity, and the singularity requires a coupling constant renormalization. Therefore, it's a good model for some of the ideas. And it's not the one I'm going to talk about, slight extension of it. Okay. It turns out that this problem is a scaling symmetry, and because of the scaling symmetry, I don't know if I'm just, maybe this is good. Because of the scaling symmetry, if we have a bound state, we have infinitely many, therefore H is not bounded from below. And the only way that we can rectify this is by renormalization. And we know that there is really no actual delta function. It's actually a model. It's not true delta function potential. It's the model is that you have a very sharp potential, very attractive sharp potential, and the wavelengths that you work with compared to the scale of this potential are so much bigger that you don't see the structure. And that's sort of the effective field theory point of view. Okay, so that's essentially what I would like to talk about. Incidentally, we did the work on point interactions on manifolds in 2006. Unknown to us, there was exactly the same work by Brüning and Gaylor in 2000, and it was not known to me. Brüning is an analyst who works on pseudo-differential operators and an expert on these things. And they just did it exactly what we did. Basically, they did the same thing, but we didn't know about that, and the referees did not alert us about this work. So, but then much later, I learned about this work. So the problem that I'm going to talk about is a slightly different version. This is something that we published with Çağlar Doğan some time ago, and it's the following version, which is very similar to, it's essentially a delta function, but you take a Klein-Gordon particle, and a Klein-Gordon particle just sees kind of a potential. It sees a point, and it just tests the point. The particle goes and sticks to the point and then comes out of the point, which is like this is like a relativistic way of seeing a potential. And then you have a coupling constant for every point. So this is like a point source interacting with the field. But of course, normally you would have not just the annihilation and creation operators, but you would have the field. So this is kind of a non-local version. So it's not exactly completely relativistic system in that sense, but it's sort of an approximation. If you're in the low energy limit where the particles have high kinetic energy, but not the interaction is not causing particle creation. So that's kind of the limit. And that's allowed because it's essentially you have these limits, and the solutions will tell you up to what point you can push this idea. Okay, so that's sort of the model that I'm going to give you a brief. The reason that we work on a manifold is, one, you can do it, as I said, and the other thing is that it's nice to have kind of infrared cutoff. If you work with compact manifolds, it's good to have an infrared cutoff because many of the theorems that I'm going to claim are harder when you have continuous spectrum. Remember, in mathematics, continuous spectrum is always a problematic thing to deal with. It's not that you cannot do it, but it's much harder. Okay, so let me just give you a brief reminder that on a compact manifold, the Laplace operator has a discrete set of eigenvalues starting from 0 and then going up to infinity. And you just do the standard canonical quantization. Instead of momentum k square, you just have the eigenvalue, okay? And then the eigenvalue of the Laplace operator. And this truncation that I used to build the model is essentially is called the Tam-Dankov approximation. In the 60s, this was an approximation proposed in field theory, which turned out to be not very successful. But then it was revived in the light front by Wilson and company. And so it turned out to be a useful approximation in the light front. So it turns out that it's better to study these things with the heat kernel, because the heat kernel is a natural geometric object associated to Laplace operator. It's essentially the imaginary time Schrödinger equation, and the diffusion, you can think of it as a diffusion. So it solves this heat equation, symmetric fundamental solution. As time variable goes to 0, you get the delta function, and it satisfies this composition property, what is called the essentially semi-group property, that in time the convolution in time is the same. Well, you basically integrate over. I'm sorry, this is the z variable because I have a typo. You integrate over the intermediate variable z, and you get this expression. And on the compact manifold, you have a uniformly convergent expression 4, which you can express this heat kernel exactly in terms of the eigenfunctions and the eigenvalues of the Laplace operator. And on compact manifolds, usually, I mean, it's not obvious that you can normalize this to 1, but we expect that you can normalize it to 1. But so non-compact manifolds, that's not obvious. On a compact manifold, it turns out that this is always true. You can always do it in a compact manifold. Okay, so the main identity that I need is this number 8, where the Green's function for real values less than 0, you can actually represent it as the integral of the heat kernel. So that's a nice thing to have. So, well, you can also do it for any operator, basically. You can think about a heat kernel of an positive operator H0, and you can relate the Green's function to the heat kernel of that operator. So that identity 9 is something that is useful in many ways. Okay, so the other thing which is very useful is that in short time asymptotics, this is the basically something found by physicists as well as mathematicians essentially independently. This was found by Dewitt and Seeley, and then also Plemelgen, Mikusan-Drash, I think, in the math literature. So this is an interesting thing where the coefficients, the diagonal heat kernel expansion coefficients, are universal polynomials in the curvature, and it's covariant derivatives. So it's this is a very useful expansion to have. For our purposes, this is not going to be used except to justify the normalization. Okay, so these are the universal coefficients. Now, the idea that we had was to regularize the interaction. Instead of the delta functions, notice at 11, k epsilons, if you let epsilon goes to 0, is exactly, because then it reduces to the delta function, you will get phi minus ai and phi plus ai. So this is a regularization by smearing out essentially the operators with heat kernels. Therefore, you could sort of define a regularized Hamiltonian, and then you take a limit. That's the idea. Now, we will use an orthofermion technique, which is developed by Rajiv, but this essentially, it's not essential in this particular problem. It's just because a lot more easier and aesthetically more pleasing to use these things to get the result. Nevertheless, you can do it without these operators. There's something called the Schur complement formula, which you could use directly. But this algebra, which is called the orthofermion algebra, given by 12, essentially it says that you can only create one orthofermion, and then the orthofermion you can create and destroy. If you try to destroy twice, or you try to create twice, you always get 0. And if you just look how many orthofermions you have basically one orthofermion subspace projection is what you get. Therefore, it's a very interesting algebra that you could only generate one and you cannot generate more, and it doesn't satisfy commutation relations. It satisfies basically operator product relations. There is a famous algebra called Kunz algebra in operator theory. So this algebra is sort of a related algebra to those infinite dimensional algebras. But in a way, this is a simple trick to obtain certain inverses of your operators. So the idea is you extend your Fock space because we have this Klein-Gordon particle. You extend your Fock space by no orthofermion in 13. You have no orthofermion or one orthofermion, and you have the usual bosons. Now, at the end of the day, I'm going to restrict myself to a single particle. So as I said, this is a bit of an overkill, although the model can be generalized to more complicated situations. So I like the operator, the second quantized language, because you could there are possibilities to extend this model. But it turned out that all these extensions are quite hard to solve. I tried many of these extensions. In any case, I want to keep the extension. It turns out that you could write down the resolvent, which is the Green's function in physics terminology. You can write it down in this extended space with this truncated cutoff system, 14. You see that there's an epsilon. Epsilon corresponds to the cutoff that we introduced. So this is a regularized Hamiltonian, no divergences, no problems. And this beautiful trick invented by Reggie allows you to just write down the resolvent in two different ways. And one of these ways of rewriting it in 0 orthofermion, he calls them angels. So I don't want to just leave the name outside because he thinks it's a very beautiful construction. So it gives this whimsical name. So essentially, if you restrict yourself to 0 orthofermion sector, that's exactly the Green's function that you're interested in. And you can calculate it in two different ways, thanks to the algebraic structure. And then you get formula 16, where the A is essentially the free Green's function for the Klein-Gordon particle. B is this corner, which if I can go up, B is this corner in the off-diagonal terms are B's. And then you could basically take this expression, and there's a key operator, which is phi inverse. This phi turns out to be essential construction, because if you look at A inverse, it only has poles at where the free particle has. So any bound states, therefore, would actually come from the zeros of phi. Okay, so the zeros of phi, because we have the phi inverse, so the point at which phi inverse is not defined, that's going to give us the poles for the Green's function. And that's how you can get essentially the information about your system, because this problem is going to have bound states, and that's what you have to make sure that everything works out. So this is called the principal operator, and it's this object, and this is essentially a projection of the resolvent of the extended operator onto the 0 orthofermion. And as a result, what we claim is you can remove the cutoff, and after you remove the cutoff, you actually define a self-adjoint Hamiltonian. Now let me put this into perspective, because I introduced a cutoff, and then I have an infinity that I have to remove from the coupling constant. And this infinity, removing the infinity through a coupling constant through definition, you do some operations and you get a new object. But then you have a formula that you remove an infinity. And how do you know that you actually define a Hamiltonian? That's not an obvious thing. So here is our operator written in this messy manner simply because we're working on a manifold. If you write this on a flat space, things will look a little simpler. But the essential idea is that this part, the last part, is not going to be used in a one particle sector. Essentially, the coupling constant which appears in the first line, and then there is some self-interaction type of thing which you have to study, and then you get essentially a divergence from here which you have to cure. And the last part, as I said, is not going to be essential for our purposes at the moment. To do this, you use this beautiful identity in operator theory called subordination identity, that because the Klein-Gordon particle is essentially it's like a square root, it's some sort of a pseudo-differential operator. So you want to make sure that you can relate it to something recognized, and that this beautiful subordination identity allows you to convert it into the Laplace operator. So I can just go to the Laplace operator. And what you notice at the end of the day, that this nice cutoff allows you to combine these heat kernels, and then you get this epsilon, which you can then use to cure the divergence, because as epsilon goes to 0, you're going to pick up a divergence. And this is the one, in the case of the one particle case, this part is going to be dropped out. So you don't have to think about that A dagger A part, as long as you don't work with many particles. Okay, so this is essentially what happens. You get the cutoff, and then now you can see 1 over g squared part. You can cure it by choosing 1 over g squared properly. And the way 19 shows you that there's a logarithmic divergence. Therefore, you can pick it exactly to cancel this, which is as shown here. If you just cancel exactly this divergence, to cancel it, of course, you have to introduce a mass scale, because the theory 19 has this e to the minus u m squared ku a I part, which sort of causes the divergence. I keep it to be able to cancel the divergence exactly. But then there is an extra part which you have to pick. What's the binding energy of that delta type interaction? So that's where you make your choice. And the idea, physical idea, is coupling constants are things that you don't actually measure. You measure something else. You measure either scattering amplitudes or bound states. So instead of giving us the coupling constant, you could equally tell us what's the binding energy of that single location. If a particle is captured by that single location, you could tell us what is the binding energy. You could also tell us what's the scattering, something like the scattering length. Okay, so not to specify the coupling constant and trade it with something else is not a strange thing. This is actually what happens in typical measurements. So that's what you pick, and there is, as a result, and here are some calculations to justify that you work with one boson and everything works out nicely. So let me just skip that. So at the end of the day, restricted to the one particle Hilbert space, we have this Green's function, what mathematicians call resolvents. The Green's function, which is expressed, as you can see, with the free Green's function plus a correction part. And the correction part has this phi inverse. And the phi inverse, this matrix that we have, this can be turned into a matrix. Now, the I and J label the points at which you have this interaction. So the points 1, 2, 3, 5, whatever, every one of them where the field or the particle can stop, interact, and leave, those are the locations. So what it does is you propagate, in a way, the propagation of the particle. If you think of the Green's function like propagating a particle, you're basically propagating it, or you're basically propagating, visiting a site. This says, well, remove the particle. Now, look what it does, phi inverse ij. Look what it does to the particle. Put it back and propagate. So in that sense, this is like an exact, this is an exact formula, by the way. This is like an exact expression for taking care of these points, the interactions at these points. Now, as I said, you wanted to look at this matrix, the inverse of this matrix. Therefore, whenever you don't have an inverse, you would have a problem. And to understand how this problem appears, you have to look at the eigenvalues of this matrix. This matrix turns out to be, if E is real, if you pick E to be real, this matrix is actually a nice Hermitian matrix. Therefore, you actually have eigenvalues. It's a finite matrix. And you can study how these eigenvalues behave. Moreover, whenever these eigenvalues hit the zero, you have no inverse. Therefore, most likely you hit a bound state. Okay, so the advantage of this formula is because it's the inverse of phi, directly phi itself, the eigenvalues of phi, whenever they hit zero as a function of E, then you possibly have a bound state. Okay. Now, another beautiful thing about this, by the way, this is on R2 what you get. Okay, so you can actually explicitly find the elements of this phi on R2. But for R2, you could justify many things because the spectral theory of R2 is nice, as the Fourier transform is an isometry. Therefore, everything nicely can be done. But on other compact, non-compact manifolds, this becomes very hard. So that's why I'm just going to stay mostly on the compact side. Okay, so how do we know that this defines a Hamiltonian? Because I just give you, notice that in this formula, I told you that the other side is H minus E inverse. But I don't have it. I don't have H. I only have the right-hand side, which is a formula that involves H0 minus E is inverse and some combination of things. Okay, so then I kind of need to tell you that, or justify, in the old school fashion, justify that this formula indeed defines a Hamiltonian. Okay, and for this, the first test is the resolvent identity. If it's actually a Green's function, then it has to satisfy this identity that you have to check that it does, and it does, of course. But that's not enough because these things are called pseudo-resolvents in the math literature. People actually knew a lot about these things. So we didn't have to invent new things. It was already there. And so you can just look at the family of these operators. And then there's another test. There are many different ways. This is one test that I like personally. It may not be the best way to do it. You need a decay condition. So you pick a family of complex numbers that the absolute value of which goes to infinity. And you have to look at this expression for any vector in your Hilbert space. This expression has to go to zero, the norm. So basically this expression hits on a vector and you look at the norm of that vector. And this has to go to zero as your sequence of complex numbers diverge to infinity. So that's a test that they invented. If you have it, then you do actually have a true resolvent. That is an operator. Moreover, if this thing, actually the adjoint of this thing is equal to complex conjugate RE, which is written here, the adjoint of resolvent is equal to RE complex conjugate, then in fact, this operator that you have is actually self-adjoint. Okay, so we have to verify these things basically. Okay, so what we did in a joint work with Erman, Doğan, and myself, we actually did verify these things. But to be able to verify these things, we also wanted to show that the Hamiltonian is bounded from below. So we had to find a critical value beyond which, if you lower this, you actually get an invertible operator. So therefore, there are no eigenvalues that will cut the zero beyond this value. So, and in order to do this, we need a lot of results. Basically, we have to show that the this matrix is a holomorphic function in a certain, at least in a certain part of the complex plane, because you have to use many technical things, and to be able to use them, how do you know all the things you claim are correct? Well, you have to prove as much as possible all these properties. And one test for this is this thing, which I show here, that if you have a function which is continuously differentiable on some open subset of the real axis, and it so happens that this inequality is true for any compactly supported complex valued function on this interval, then there is actually an analytic continuation of this function to a symmetric relative to the real axis open set in the complex plane. Actually, it is basically up onto the upper half plane, and the region of analyticity actually includes this open set delta, and you can analytically continue this from the upper half plane to the lower half plane basically by Schwarz reflection principle. So why we need these? We need that because essentially we wanted to know, if I show you the spectral structure from here, so basically the spectral structure is essentially something like this. So we have possibly the free part, which actually has some poles over here, and maybe there are possible bound states. But then beyond this point, you have a region where there is no problem that appears. So you start from this region below this possible poles of phi inverse, and you verify this identity along this line, this inequality along this line, then you know that there is what people call a Nevalina function, which has a continuation to the upper half plane. And then you know that it is all analytic on the upper part, and by Schwarz reflection, it can be continued to the lower part. And there is possibly some poles along this part of the real axis. So that's basically what you prove. I mean, these are things that analysts, of course, know quite well. And they, by the way, these things were done pretty much in similar ways for the ordinary delta functions on the flat space. For flat space, ordinary delta functions, there is tons of work which indeed exploits all these things by people like Albeverio, Holgekron. I mean, there's even a book about these things which uses many of them. They're very hard to read because they're written by mathematicians for mathematicians, although they claim that they're written for physicists. But they're very hard to read because they use lots of technical things. Okay, so another thing that which we claim is that as we have these holomorphic structures, what is essentially the ground state? Now, for this, you test the following thing. You look at the eigenvalues of this operator phi as functions of the real variable e. Remember, they are actually complex holomorphic in E, but not in every place except part of the real axis. They are holomorphic functions. So let's suppose that we're in the region where we could actually look at the flow of these things with respect to E, and you see this, that they actually decrease as you change this parameter E. So what does it mean? Okay, let me just go to the other figure. Okay, it means the following thing. Okay, this is an eigenvalue flow, which, of course, now my computer stuck. Okay, so maybe it will come back again. Okay, so here is what happens, that you do actually have these eigenvalues of phi. These are eigenvalues of phi, and that's how they change as you change your scale E. Now notice the lowest eigenvalue of phi indeed cuts the real axis first. Because it cuts the real axis first, that's the smallest pole that you get in the phi inverse. And if you want to find the ground state energy of the system, you look at the first eigenvalue of phi, the smallest eigenvalue of phi, and you look where it cuts the real axis. That's going to give you the answer. Okay, so that's the observation. Okay, this flow. And Therefore, that's a good thing to know. And then you could actually calculate the ground state wave function. You have an explicit formula where these AI zeros are the components of the eigenvector that corresponds to the ground state E star. I should have said that it's E ground. For some reason, I kept E star. Okay, now let me just make a slight comment that in quantum mechanics, we know that even if we have symmetries, there is no symmetry breaking. Remember, in quantum mechanics, you could have a symmetric configuration. And you could imagine that, for example, a discrete symmetry that you have, you could try to pick a special wave function which would just break the symmetry. But of course, we know that due to tunneling, this would not stay. It will actually exploit possible decays and eventually would find an energy state which is actually lower. And this is the rigorous proof is actually due to Cutoff, famous analyst and operator theorist in quantum mechanics. Cutoff gave the first rigorous proof of non-degeneracy for regular potentials, including things like Coulomb potentials, etc. And you can read it in Reed and Simon, for example. And this is sort of a generalization of the finite dimensional matrix problem called the Perron-Frobenius theorem, well known in finite dimensional matrices, what's called the stochastic matrices. It's essentially a generalization of this. And the Perron-Frobenius formula says that if you have a matrix, the elements of which are all positive, then there is actually a maximum eigenvalue. And then this maximum eigenvalue this is unique. There is a unique largest eigenvalue. And the members of the there is a basis for which the components of the eigenvector become all positive. You can pick them all positive. So that's an interesting possibility. So it says that in our case, we have a singular quantum system, but we can use the phi matrix because remember the bound states are coming from the zeros of the phi matrix. We can exploit properties of the phi matrix. Therefore, going back again to the Perron-Frobenius formula, remember, quantum mechanics has a generalization of Perron-Frobenius formula. Now, that in the singular case doesn't work because there the potentials are assumed to be regular potentials. If you want to extend it, you use this phi matrix, and then you go back again to Perron-Frobenius for phi matrix, and then you exploit that, and you can just show that again there is a unique ground state. In this case, of course, you just flip the sign because everything is minus, but it doesn't matter. You can flip the sign. So there is a unique lowest eigenvector.
And you have 5 minutes left.
Yeah, and there is a unique lowest state. And that shows you that even in these situations, we have a ground state wave function which is unique and therefore non-degenerate. Okay, so we do have a generalization of this for such singular problems as well. Okay, we wanted to extend, okay, this is a modest problem. We wanted to go a little bit further with something called the Lie model. Actually, this is not exactly the Lie model. This is sort of the simplified version of the Lie model, sometimes called I think the Feldman model, or also called Wigner-Weisskopf model. So it's essentially the following problem. I'll just hopefully say it in 5 minutes. It's the following thing. This is the non-relativistic version. There is a relativistic version of it, which we have done recently and couldn't publish, and Mel Teminel is one of the co-authors of. That's essentially her thesis. This is the non-relativistic one. It says there is an impurity, there is a single impurity, and you have a bosonic field, and the bosonic field couples with the impurity. These type of models are very fashionable in optics because you have an atom with 2 states and the photons coupled to it. So it's kind of a similar thing. This model requires the mass of the impurity, which is mu epsilon here, to be renormalized. Okay, so now I'm just going to skip all the things because I just want to tell you what we have found before our chair lady gets really upset with me. So Again, we find the formula. Let me just try to show you the formula. Hopefully I can show you. Okay, here is the formula. The principal, we get exactly the similar type of construction. You get the principal operator, which has the usual Hamiltonian, H0 minus E plus mu, plus a kind of a correction, which is small compared to the leading operator. And then there is a minus lambda squared, a potential part. Now remember, this is a many-body system, so therefore I have more components than the previous problem. And you again have to have certain properties of this operator will tell you what goes on. So what is it that we have done? Again, you look for bound state solutions as zero eigenvalues of this operator. And the results, very similar, very analogous. You get again flow, spectral flow of these eigenvalues. That means the lowest eigenvalue will cut the real axis. That will give you the ground state energy of the system. There are many results that we needed to use, but one of the things we need is to make sure that we have some of the formula that we can use requires these operators to be a family of holomorphic self-adjoint family of type A. This is cutoff terminology. So is it true? Well, it takes a painstaking amount of work to actually justify the following things. The resolvent satisfies the resolvent identity. It's one of our results. We wanted to check that it actually satisfies this thing, which makes it a self-adjoint operator. Now that's not easy. That to show that it's a holomorphic family of self-adjoint operators, it takes some work. And then that's what one of our publications, we have done this for the simpler model, which is the non-relativistic model. And you use many technical results from the literature, such as Wu's theorem and the invertibility and things like that. And the recent work, I'm just going to skip, and the recent work by Ünal, based on the thesis of Burak Kaynak and then later Meltem Ünal and a student in CMU, Yesuke Jacques Varal, we actually did these things for the existence and holomorphic family of self-adjoint type A. Okay, so maybe that's a good point to stop before our chair lady would be very unhappy with me. So thank you.
Let's thank our speaker for this great talk, and thank you for your kind considerations. So are there any questions from the audience?
If you talk about analysis, nobody is happy. That's the end of the talk. You know, the analysis talks are not things that people like. But as I said, I mean, I gave an old school talk about essentially in the tradition of Glim and Jaffe, and nowhere comparable to what they have done, of course. I mean, these people did amazing works. So this is much, much, much more modest amount of things. Okay. Thank you.
Can I ask one small question? I mean, it's a silly question.
No, none of
it got too technical for me at a really earlier point. So, if you have singularities in your system, like delta function singularities, or some other type of singularities, and there is an interacting system, and you want to solve the solution, find the solution to this system. So, at some point, you gave us a formula, right? You find the free Green's function.
Yeah.
And then there is this additional term.
Yeah, that's essentially.
There's a particle incoming, and there's a sort of like another black box in the spirit of maybe the QFT type of thing, and you have an operator there, the phi inverse thing.
Yeah.
So can you, in general, come up with solutions of this form, or
no?
Okay.
No. I mean, like these type of interactions are very special. You actually in a way cheat a little bit. I mean, I cheat a little bit in the sense that that these problems have a conserved quantity. You actually restrict your Fock space into a conserved quantity region, so it's not the full Fock space. Now, the main problem of interacting quantum field theories, and that was the reason why Glim and Jaffe even, you know, like Glim was a child genius. I had a dinner with Caddison, who was the advisor of Glim, and he told me, unfortunately, Caddison passed away. Caddison told me this young man came into class, took the operator theory class from him, and he posed a bunch of unsolved problems, and he solved them in 2 months, one of them, and that was his thesis. He was a brilliant man. So with Jaffe, they went into two-dimensional actual field theories where you have the full Fock space. And the great accomplishment of their thing is Yukawa theory in 2 dimensions. They have the full Hamiltonian time evolution completely rigorously done. But they gave up for the 3 dimensions, because for 3 dimensions, this became impossible. So they switched to Osterwalder-Schroeder Euclidean Schwinger functions. And their book essentially about the 3-dimensional thing in the Schwinger functions, not in this way. And even that, because if you want to push it to 4 dimensions where the real thing is, that doesn't work. Okay, that they couldn't do it. You know, they gave up eventually. Okay.
Thank you, John.
Sorry. Thank you.
Okay, I guess there are no further questions.
Okay, thank you very much.
So let's thank our speaker again. Hocam
Thank
çok
you.
sağ olun.
Thank you, Hocam, again.
Thank
you, Hocam.
Okay.
Thank you.
We'll give a 10-minute break and then come back for Meltem'ine.